properties of the polymeric material, ceramic material, as well as condensed matter, which have very high significance proportion for the magnetic material study. As this is the best known university in our eastern part of the UP, and it's an education hub from the centuries. So we have some fascinating tool that located in our institute, and time to time, depending on the need of the experiment or scientific cases, we travel abroad internationally to assess some advanced facilities such as like a free electron laser, synchrotron sources, neutron sources, as well as muon, to characterize the various advanced material that we fabricate in our lab. So personally, my lab is focused towards the devices part. So we grow this multi-layer sandwich of material using alternating ferromagnet, anti-ferromagnet, or even the spin valve structure sometime. And the objective of our work basically exploring that how you can perform the device functionality by changing the various material, its composition, its thicknesses, and so on. So apart from this devices structure, there are some new dimension in magnetism has emerges that basically utilizes the topological feature of the spin. So that we also going to see briefly. And nevertheless, we have also new emerging dimension of the neuromorphic devices. So these are the some like a wide area that we work in our small lab that what is located in the our school. So basically, today's presentation, I will going to highlight the magnetic film and the multi-layer, some growth technique, and how you can characterize some uniqueness of the magnetic material using some advanced characterization tools. And also, we are going to show some specific characterization of this material. So as I mentioned briefly that evolution of the quantum mechanics, actually that's what we understood that tells about the superposition, interference, entanglement, and the wave particle duality, and some new concept of the spin, fermions, bosons, and obviously the uncertainty. These were the basic understanding of the quantum mechanics that one can assess. And this can be assessed at any dimension state that's available by the nature. It could be atomic scale, or it could be also at a universal or interterrestrial scale. So how this actually work? That's still not well understood that how at a different length scale, same principle applied. Because the nature of the force, that what we have seen, we know that there are gravitational force working on in terrestrial body, but atomic scale, we have a different type of force that control the mechanism. But quantum mechanics is valid for each length scale. That's the uniqueness of the quantum mechanics. But for a general people, quantum mechanics is still a riddle and hardly have been understood. But it's one can see that quantum mechanics is the something that hardly understood, and it is have ability or exceptional ability to describe the all possible phenomena that happen in the material. So the best way to appreciate the quantum mechanics is shown by this two-dimensional example. That's what we call as a double slit experiment. You pass the electrons like a firing electron to the double slit, and you see this fancy pattern of the alternating intensity that can be also replicated using other particles. So these two experiment actually the initiated the basic conceptualization of the quantum mechanics, where people started talking about the dual nature of any entity. Yeah, so that's a great experiment that people still celebrate its a finding. So this leads behind the wave particle duality, and there are various philosophical aspects of the quantum mechanics as well. someone shows description of the classical that what initiated by the Plato, where he says, someone says that through their hand at the say Plato got it right all along when it comes to the understanding of the physical reality that how we are in cave. And simultaneously using the quantum mechanics, Niels Bohr predicted something differently. Same thing, but in a different way. There is the no quantum word, and there is the only an abstract quantum description. And in this word, task of physics is find out how the nature is. The physics concern, that's what we can say about nature. So Plato realized that applying the classical mechanics, you can understand the nature, dynamics, how things work, but the quantum mechanics at the same time describe the nature as like a still riddle and hardly understood phenomena. And one can use this concept of the quantum mechanics to find the feasible reason that how it works. So as I say, that quantum mechanics actually work at all possible scale. So here, the ability of quantum mechanics at a very small scale that have been witnessed by the community or mankind when people started bombarding the nuclear weapon in Japan, especially Nagasaki and Hiroshima. So that's the ability of the quantum mechanics, that how you can use such scientific understanding of the atoms and molecules, and you can generate humongous amount of energy in both controlled and uncontrolled way. So when it's a controlled way, you can serve the humanity, but when it's an uncontrolled way, you can destroy the humanity. Same concept. But working not only this purposes, but also describe the nature, so how the molecules and atoms actually form and how they interact with the surrounding. Not only that, now this quantum mechanics also use to store the information. So next generation computing, that what we are used to now and well studied and developed, now this will be a past thing, and in coming time we are ready to welcome the quantum computer and quantum based technology. So that's we have very exciting year ahead, but there are always certain doubt that how the technology this change the entire world and its a functionality. Not only that, there are various purposes there you can still use quantum mechanics to mesmerize the word, such as here shown as a superconductor showing a Leviton effect. So classical mechanics is unable to describe this behavior. And not only that, this give you the various possibility and make various fancy things like this bullet train and related technology, ultra fast train, that what people are still working, and in other countries they have this surface transport solution. So here also another very important aspect is a large scale Josephson junction that actually the cause of this year Nobel Prize award, where people try to find the quantum tunneling at a microscopic scale. So the same phenomena have been derived by Brian Josephson centuries, 2-3 decades back, and same concept followed by this James Clerk and other people to find. Not only that, this quantum mechanics also explain various unseen and misunderstood phenomena that happens in the cosmos. So quantum mechanics is still is not very understood, but one thing clear that you can apply this behavior in all possible length scale, which is not the case for other forces that we are aware, like the four fundamental forces that we know, they are not able to describe all behavior. So now is how one can realize this quantum behavior in a multiple scale. So especially in Cosmos, we cannot be there to witness any event. So we need to find a other solution that where quantum mechanics behavior can be witnessed, or its effect can be witnessed. So that is one part that we can try to explore the lower dimension sense that we can do. So splitting bulk material into a smaller length scale, that's quite a feasible way to explore the possibilities. So here is emergence of the this new technology, that's what we call nanotechnology. This enable to have this various possibility, and using this we are able to grow various material on a atomic scale, like here 0.5 nanometer or 0.7 nanometer. That's very small length scale that you can like in a region of the quantum behavior. And that's what actually happened. So when you design this material, there are various new phenomena that emerges that you cannot simply use the conventional theory, but you need to find certain different aspect to describe this. In the growth process, when you are trying to grow the magnetic material, there are various ways that you can grow a different type of material, such as like you can grow a nanowire on top of substrate, or you can also grow a porous material where you have implanted deliberately some desired material in the pore in compared to the other sections. So it's like you are not only controlling the material, but you are also like designing the material. So you have various ways that you can design this multiple structure. And here is the first demonstration that what I am trying to show. That the same material have been grown in a different geometry, and you can see that how their microstructure. And not only that, even later we found that their magnetic property are differ very significantly depending on the structure that we are using. So the method that generally people utilize to grow this material is called pulse laser deposition, or in short form, it's a PLD. That's a one advanced tool that you can utilize to grow a very thin film of the material, sometimes continuous thin film, like on top of substrate. Sometimes you can also make a nanostructure thin film, and that will give you a enhanced surface area. So you have all different degree of behavior compared to the continuous film. So we grow all this material using this method. So here is the phenomena that how actually atoms come and deposit from the thin film. So here is the growth process. So atom will arrive and they start forming a stack, and that will leave behind the growth in a perpendicular direction of the substrate surface. So it's like you have a plane, and perpendicular direction is a growth direction. So that's what another demonstration. So even if you don't have this fancy tool, but there are liquid phase epitaxy that you can try, or sol gel method. So they are cost effective, and even in any generic lab that you can use this method to make the thin film of certain advanced material. So these are some experimental details that how the deposition unit works. So this is the method that actually tells us about the thickness of the grown thin film. So during the growth, we apply this tool to monitor that what is the maximum thickness that we have already deposited. And this is work on the quartz system. So quartz material is actually used here to monitor the thickness, and as you deposit the mass vibration, so this is nothing but it's a kind of a resonator, and when you deposit more and more mass, so accordingly you are changing the vibration frequencies or resonance frequency, So you can see that what is the thickness actually you have drawn on the top of material. Quickly, we can find a recap of this evaporation, physical evaporation based method. So that's have some limitations, such as like accurately controlling alloy and compound are difficult, because if you have something light element, suppose like lithium or oxygen, so controlling their stoichiometry, that's always a challenging task. So that's not very feasible method for that. And also, you have no means to do the in situ cleaning for the substrate to have a very clean sample. And there are also, if you don't have a expertise, then variation of the deposition thicknesses is also not very easy. So using this method, you have a possibility to do the stacking of material. That's what has been shown. So this is one unit of stack where suppose iron, that's a green one, and white is some non-magnetic material, suppose silver, then again iron. So iron, silver, iron. So these are the two materials separated by one another material, and we all know that iron is a ferromagnet, and when you are putting this aluminum, which is a non-magnetic material, so you are separating these two ferromagnet using this spacer layer. Not only that, apart from this sequence, you can have this stacking. This sequence you can repeat. So the main benefit of this repetition is like you are enhancing certain property. Same way is like you have a multiplication of the effect. So ultimately, you are amplifying any event that occurring at a small scale. So this type of staking enable you to enhance those phenomena that occurring on a very small scale. This staking enable you to do this amplification of the effect. And here, this have the same thing that what we talked about. Like this is the same that what we were saying. So in this sequence, we have found iron, and it is separated by chromium, and that's the founding structure of the spin valve. That's another important phenomena that this Albert Fert and Peter Grunberg have demonstrated it the first time. So when you have the two ferromagnet, so there is the possibility that you can change the magnetization of the both in a two different way. One, when the magnetization of the two ferromagnet material are parallel to each other, like one is showing upward, another is showing downward here. And in this case, when two are upward, so that we will call a parallel configuration. So here, both magnetization in same direction, here in opposite direction. So this will leave behind a new phenomena that what actually called the GMR. So depending on the magnetization arrangement on this two ferromagnetic layer, overall resistivity that you measure in these two cases, they will be differ. And this difference in the resistivity you can control by changing the magnetization of a material. So ultimately, what you are doing, you are affecting the transport behavior of a material by changing the magnetic field. So that's a uniqueness observation that these two people shown. And for their work in 2007, they awarded with the Physics Nobel Prize. This is the structure of the devices. That's what I was talking about as a GMR sensor. So here you have two magnetic material, and it's separated by this white color. That's a spacer layer. And this spacer layer are supposed to have a very small thickness in the range of the 2 to 3 nanometer, or even smaller is better. If you see the effect is very small, So you can do this stacking of the sequence. So you can amplify this phenomena in such devices. And this is how their experimental data look like. So this the first case that Goldberg have reported that if you have the magnetization in anti-parallel configuration, you have a very high resistivity. But now when you go to the saturation side, this side are negative saturation side, the resistivity is order of magnitude is smaller. So that's the difference of like in the same material you can generate two resistive state. So that's like very much like our electric switch. That's what we use in our daily life. In our houses. So it's like ability to turn on and off. So high resistive state is off and low resistive state is on. So like when you are in parallel configuration, you can say that it's on state, and when it reaches to the anti-parallel, it's off state. A very similar observation made by the Albert Fert, but it's an independent observation from the Peter Bloomberg, and they did almost simultaneously but independent work. And here he shows this by not only using a spatial layer, but also he tried to demonstrate that how by reducing the thickness of this spatial layer, you can actually amplify this effect. So this is the different observation that what Goldberg have shown. So the reason for this difference of the resistive state in a tube is actually explained by the difference of the density of a state or up-down spin in a ferromagnet. When you have like a paramagnet material, so both spin up and spin down density of state are identical. Now, when you go to the ferromagnet, so ferromagnet known to be there will be one preferred direction of the spin, and that means one type of spin are in majority in compared to the other different type. So that's what actually mean. So this you see the difference in the density of state or upward spin and the downward spin, and this lies behind the various uh, uh, different range of the resistive state. That's what we are seeing in the devices. So this is another demonstration that how the density of state evolve when you do the magnetic layer alignment in anti-parallel or in parallel. So this structure can work like as a device in form of a switch that you can control by applying a magnetic field. So that's remarkable. So even you don't have to touch the switch, you can use the magnetic pulses and they will turn into on to off and off to on. So that's a remarkable observation that what have been shown in these devices. Not only that, if you can use this spatial layer as a insulator material. So now I'm passing a current along this direction of the arrow, and in between this white layer, suppose it's a insulating. So that will leave behind another phenomena. That's what called tunneling magnetoresistance or TMR. So the difference between tunneling magnetoresistance and the previous case, what we call the GMR effect, that in a GMR sensor, we have a conducting material, but it's a non-magnetic. Here, we have a insulating material and non-magnetic. So now when we put an insulator, simply if you think about the classical description, so current shouldn't pass through across this body. But since due to the quantum tunneling, if you have a well-controlled thickness of this spatial layer, then there is always some finite possibility that electron can tunnel through this barrier that have been shown in white color, and conduction can take place across these devices. So this phenomena, if you can observe at a micro scale, and that will enable you to win the Nobel Prize. That's what this year Nobel Prize actually awarded for this quantum tunneling behavior on a microscopic electronic devices. And in previous slide, that's what I saw. It's a nanoscopic devices, so nano length scale devices. But these gentlemen have demonstrated the same tunneling behavior using electric circuit on a microscopic scale. So this is like a designing a artificial atoms. Yeah, so it's like you have multiple atoms sitting at a different places. Even they are separated on a microscopic length scale, but still quantum tunneling can be realized. So that's a great achievement by these two people. So here, not only that, it will also initiate various other interesting behavior. Now you can try to manipulate the thicknesses that located are shown in this blue color. So this will leave behind various other phenomena due to the variation of the interlayer in between these two materials, like the changing of the magnetization direction. So not only that, you can have this anti-parallel antiferromagnetic coupling, or you can also have the biquadratic coupling. So here you are doing parallel, but field direction is like a 90-degree. So that's a different arrangement than this one. So here both are in parallel or anti-parallel, but here they are somehow field that you have applied or magnetization are perpendicular. So they will give the biquadratic coupling. Not only that, you can have nanostructure behavior. So, or you can also tweak the thicknesses of the interlayer. So to do that, people have designed various material system where you can tweak the interlayer and form this wedge material. So here you can see the nature. So it is not perfect plane, but you are forming a wedge shape. So the thickness, if I measure here, is a 10. If I measure here, it's a 50. If I measure along this direction, it's somewhere 80 or 75. So the wedge will allow you to manipulate the interlayer exchange coupling between these two ferromagnetic material. And that's what have been shown here. This sandwich will change the entire length scale in vertical direction, and that will give a different phenomena. That's what called the oscillating nature behavior. That's what have been shown in this one. So electron is actually propagating through these two ferromagnet material and coming across this insulating layer. And depending on the thickness of the insulating layer, as well as the arrangement of the magnetization in two layers, this electron will feel a different type of scattering in a two different scenario. That's what we call parallel alignment and anti-parallel alignment. Depending on this white arrow dimension, these two red bars that have been shown, they are actually part of the ferromagnet, and white arrow are showing the direction of the magnetization. In this case, we have a parallel magnetization in both layers. Here we have an anti-parallel magnetization. So this will leave behind a different degree of spin-dependent interface reflection or scattering that taking place in this quantum dimension. So you can consider it's like a quantum oscillation that bound to this surface potential. And that's what actually this demonstration here. So you have this surface potential, and in between electron are trapped. And due to this trapping of electron, they behave like a charged particle under a potential barrier. That's the problem that we have seen in this quantum mechanics quite often, that you have a charged particle find its eigenstate and eigenenergy. That's conventionally what the way we learn the quantum mechanics. So it's a very similar behavior that you can see that there are various energy level where electron can occupy depending on the kinetic energy that it gain due to the multiple scattering, due to the trapping, due to the surface area and the trapping. So now if we compare the degree of resistivity in parallel, resistance parallel and anti-parallel configuration, so you can design a switch, and that's what we call a GMR sensor, or a giant magnetoresistance sensor, or in simple language, we also call them as a spin valve, so a spin switch. This is the first demonstration that I was talking about, in this more detail about the spin valve, and with the it's a spin configuration. So not only the resistivity that changes, but overall magnetization of these devices is also changes. So now instead of one ferromagnet, like here I have a 7 nanometer, and on top there is the 6 nanometer. Now the magnetization of this entire devices is not going to behave like a pure ferromagnet, but this device magnetization property will be coupled through this interface. So now two ferromagnetic, it coupled through the copper, and this will give this kind of magnetic hysteresis. And if you compare to the magnetic hysteresis that a generic ferromagnet shows, so they always at zero centered and well symmetric, and it's going to the same value in the negative saturation and identical value to the positive saturation. But here, if you see the entire device magnetization, that's completely different due to the interfacial coupling into the two ferromagnetic material. And that's again that how this mode predicted this resistivity model due to the spin-dependent scattering. So R parallel and R anti-parallel configuration, and this giving a huge change in the resistance of the various material. Okay, so now this can be also utilized for various applications. So like currently we are running a project from the funded by ISRO. So design a magnetometer that can sense the magnetic flux and stray magnetic field that coming from the cosmos in space. So this device have a very beautiful application, not only that we are seeing generally that taking place here, but also it can be applied to the various other places, such as like I talked about the project from the ISRO, where we are trying to fabricate a sensor that have beyond this planet application, as like using the interterrestrial magnetic field that all the day and night popping out on our planet. So what is their source? What is the magnitude? And this kind of measurement we have planned with doing with the our national mission funded by ISRO. So here we have a brief design that how this device actually look like. So from the down, you have a current bus line that passes that can work like a charge carrier. And in between, you mount these magnetic devices, and you pass the current and see that how the resistivity changes when you change the magnetization direction. So that's a typical layout of the GMR sensor. And here, that's a relative size that it looks like a very similar to the tennis ball. So entire hard drive disk that uses this GMR concept, and this device is actually the main source of the reading and writing information in the hard drive. And that's what you can see, this tiny mechanical arm. And so this is the arm, and top is here somewhere is a GMR sensor sitting. And this is the disk where information is stored. And if you look the overall size, I think you must have seen in a broken of your computer or laptop. So entire this floppy size that's look like in old era, that's identical. But floppy used to have storage ability of the some 700 megabyte, but here you can have a terabyte storage. So that's a benefit of this GMR sensing of the storing and reading information using this technology. These are some various structure and how this technology have evolved by various big tech companies, and they are trying to improve that how small devices you can keep fabricating. So let's begin from the top side. So here first you started with the in micro range, then you reach to the nano, and now you can just keep thinking, and now you are reaching to the somehow the nano dimension. So always there is some size restriction that you can't go beyond a certain range. So still most of the GMR sensor are saturated to this region due to the complexity of this GMR devices, because this is require more than one material. So this is the multi-layer structure. So minimization of its size, that's another challenge. And but people are able to minimize to the 10 nanometer length scale, and below that value, that's not very feasible. So people are trying to find it's an alternative. That what can be alternative of this storage mechanism. So these are the two positive and negative assets for the current, and that's what have been proposed by Solowski in this very popular paper. Uh, and this paper predicted that changing of the magnetization, even you cannot use any external field, but you can use the same current pulses to change the magnetization. It's like here you are not applying magnetic field, but passing a polarized current, and this polarized current changes the magnetization of material, and that enable you to switch the magnetization from parallel to the anti-parallel, and that will drive the switching rather than applying a additional external magnetic field to the material. And that's what actually give us this RAM devices storage that we are using in our devices. That's one another structure that how actually this assembled and incorporated with the silicon-based technology. Apart from this sensitivity of the resistive state of this quantum mechanics that uses tunneling behavior, we have another very important effect that what have been shown on this slide. That's what is called the spin caloritronics. So here, instead of passing current, you can apply the heat pulses. So you can keep the this layer, that's what a garnet thin film, which is kind of a ferromagnet, or even you can use a ferromagnet. Keep one side at a hotter temperature in compared to the other. So one can mark this side as a hot, this side as a cold. So in between, you left with the a temperature gradient throughout this material. This temperature gradient can drive another very important mechanism. That's what called the spin-Seebeck effect and inverse spin Hall effect. So these are the two important effects that you can generate. Now you are using actually heat, and with the specific material, you are generating spin current and the voltage. So that's a wonderful application of this method. And how this actually happened? This happened due to the effect of the spin charge conversion. So the spin current actually transform into simply charge current transform into the spin current, and spin current can be accumulated at a opposite edge. And due to the spin accumulation, you can have the this spin Hall effect, and you can get infinite voltage that measure. Sorry, I go in opposite direction. Yeah. So this can be also utilized in these devices by changing the magnetization direction. So how the spin and this Seebeck effect are influenced with these two different mechanisms. That's the entire devices. That's what it looks like, and this the one devices that have been reported by the group of Dasov and Brugger long back, and that's the minimum size that they were able to do the deposition using electron beam lithography. So that's a first demonstration. Not only that, here predicted various things like spintronic can be a paradigm, new paradigm for the spin-based application, and that have still very bright future. And I think there are various effects that still not well understood. So spin-based devices is actually utilized, but how you can optimize the functionality of these devices is still is a matter of debate. Like I talked about the spin Hall effect or inverse spin Hall effect, spin Seebeck effect. So you are using an external variable to improve the performance of a same material. The same way, like spin transport is very less understood. The spin pumping phenomena are how you can manipulate the spin using optical pulses. So this is the some area that hardly assess are described. So this have a wonderful opportunity for young people like you guys who can still drive, are motivated towards this direction and perform this wonderful research in your lab. So that's another demonstration that how this anti-parallel and parallel coupling are affected due to this various interlayer coupling, and the shape of hysteresis actually affected strongly by the orientation of the two magnetic material. And as we discussed, biquadratic, anti-parallel, and the parallel state. So you can see that how the hysteresis are responding into this different state of the devices. So this will bring me to talk about the other section of my presentation. That's basically is about spintronics. And the objective in this section, I will focus more towards the work. That's what we do in our lab. So here, the objective is like controlling the magnetization in thulium depth garnet thin film. So it is a well-known garnet material that used in various applications. So we have deliberately taken this yttrium-based garnet, that's what called EG, and we replace yttrium with the thulium by certain fraction, not much, to maintain the garnet crystal structure, but just changing the yttrium with the thulium, so we actually embed some more number of the spin in the garnet. So that's how we effectively manipulate a system for our magnetic application. So we replace if material is not showing the magnetic behavior as per our need, so we dope something that can make it more magnetic. And so we use thulium as a source of magnetism in garnet to make it more effective for our study. So the idea behind this work actually initiated by this three PhD who are working, who have worked. So Rajnandini, she's already completed her PhD and she's now doing postdoc in Harvard University in US. And Niti, she's doing some collaborative work in NIMS, Japan. So she's still there to work on some her PhD project. And Simran. So Simran is the main workforce for this presentation part. That's what I'm going to show. So the plan of this section is like showing that how the magnetization dynamics and magnetic damping influences the performance of magnetic material. How one can measure this magnetization dynamics and magnetic damping in material. So we have a method that called ferromagnetic resonance. So we are going to see its a setup, how this method going to work, and the formalism that we can apply to find this behavior in a material. So we will talk about these two topics, and we will show applying these two things in a garnet thin film to see that how the magnetization actually changes. And then we will move towards the effect of the thulium replacement, as well as some dynamics, and finally major finding and conclusion of this part of the work. So as you can see that this dynamics part is always associated when you apply the magnetic field. This is a very fundamental to the magnetism, that when you apply the magnetic field externally to a magnetic material, spin will process along the field and it will try to polarize with respect to the field axis. That's what actually leaves behind precession motion in the spin along the field, but this precession cannot continue forever. So slowly with the time, it will uh, decay along the this direction of the field through a damping of the precession. So you can imagine it's a very similar like a oscillator. So you first oscillate, and due to the presence of the air, oscillator will slowly keep reducing its oscillation period, and it will come down to the zero, or it will stop the oscillation. Same thing you can realize in the spin top that we used to play in our childhood. So you throw the spin torque on the ground, it will process, and with the time it will stop. So it's a very same thing happen to the spin also. When you apply the field externally, so spin will feel a torque driven by the magnetic field, and this torque will induce a precession to the spin along the field axis, and with the time it will try to come along the field axis, and that's what has been shown as a path of the spin precession. So this spin precession actually takes place at all possible time scale. So beginning from the microsecond to the nanosecond to the pico to the femtosecond. So it means there is a very significant dynamics aspect is the involved. Like how fast precession is taking place, what is the forces of the damping in your material, what is the main mechanism of the damping phenomena. That's what the key question that we try to address with our experiment. So not only that, since this is happening at a multiple length scale, so ultimately what the mechanism you define, there will be always some effect that come across to define this role of the damping parameter. So ultimately, I mean to say that this effect that what you are showing, it is going to be present at any length scale or any time scale. So determining the damping and its behavior is a very crucial for magnetic devices. So why it is actually so causing? Like currently the devices that we use for storing the information, that you have witnessed there are some serious problem. And that problem, one canonical problem is a joule heating. That's what you must have witnessed when you use this your computing devices for longer period of time. You will see that your devices is generating lots of excessive heat, and that you don't want. Yeah, so that's what you feel that this device is so expensive, but still is generating heat. This heat is generated due to this motion of the charge and presence of the Joule heating in the devices. Now the question is that is there any possibility that we can minimize this effect in the devices? So yes, there is the possibility in the form of using the spin wave rather than using electron wave. So here, actually use electron as a mean for the transportation of the information. Now we can do the very same thing. Instead of using electron, we can use the spin wave, which is nothing but it's a quanta of the spin, and that we have like wave, which is called as a magnon. So spin wave is nothing but it's a quanta of magnon, and it will propagate through the material to the finite length scale, and we can design various gate and sensing devices using a spin wave rather than this conducting electrons, which produces lots of Joule heating. And transportation of the spin wave or magnon-based devices, they don't require any, electrical bus to pass the current, so they hardly generate any heat component. So that's a transfer of spin from one side to another, or that possible throughout the lattice. But the challenge is that this spin wave cannot propagate for longer distance. For electron transportation, that's like a unique, that if you have a continuous circuit, no matter it's in a kilometer or in a millimeter, it will travel without much problem. Maybe some scattering and resistance, some decay will occur, and due to the formation of the various stages of the resistance. But in a spin wave, that's very difficult to propagate more than micrometer. So this will dissipate within the range of micrometer. So that's the biggest challenge. Or even if you don't have a specific material, their propagation length scale is roughly to the nanometer scale. So now the challenge is finding the material that have a larger length scale. And not only that, since you want to make the devices based on the switching, so you need to have very fast damping rate of the devices. So damping should be as fast as it can be. So these are the two conventional challenges that spin-based devices they offer. So spintronic still is a buzzing word, but there are various challenges, such as like how one can detail out the spin to charge conversion or vice versa. Not only that, but there are some non-collinear effect that drives behind various phenomena, such as like spin Seebeck effect, spin pumping, Rashba effect, or spin Hall effect. And then we have this two-dimensional material that gives even more complexity because they have a electronic structure. So there are a huge number of problems, I will say, that one can be worked to solve this. So like here in this type of devices, that's what we are planning. So it's a very similar structure like GMR, that devices that we talk, but with the improved switching ability. So the switching can be optimized. So that you can do by reducing a parameter that actually control the damping behavior of the spin when you apply the field. This can be done by using a method. So replace some a lattice site using material that have a lower damping parameter. So that's why we tune the thulium to replace that with the yttrium site in our sample. Coming to the technique, we utilize ferromagnetic resonance setup. So this is the structure of the devices. So here you have a magnet pulse, and in between there is the coplanar waveguide where you can mount the sample, you can apply the current, and when you pass this RF frequencies, so the spin will get absorb this RF radiation, and it will go to the excited state. something like here. That this graph you must have remember from your textbook. That's actually called the Zeeman splitting when you have a spin. So initially they are in ground state, but when you pass the RF frequencies, they will move or excite to the excited state. And this will leaves behind splitting in this two level. And now when all the radiation will get absorbed, so you will get a absorption curve, something like this. And this absorption curve will tell you a lot. What is this bandwidth and which frequency absorption occurs? So the frequency where absorption occurs, that we will call the resonance frequency, because resonance take place, and that's only absorption cross section become probable, and this uh, radio frequency get absorbed. So that's the center part is the resonance frequency. And then you have the width of this peak. That's what is the this band structure of the excited state and ground state. So that will embed it in the form of the width of the peak. And that's how you can calculate the resonance frequency by taking the derivative. So here, the center position is the resonance frequency, and peak to peak width, that's another important parameter to monitor. And this all will tell us about the damping and the resonance frequencies of a given material. So this is the device that what we have in our lab. Here you can see the magnet pieces that line, and this is the RF generator. And this blue cable that you are seeing, that's actually go to the waveguide that here mounted on this stage. And in the center part of the magnet, we have our sample. This can be also seen in this sketch. So here you have this blue stripe that mounted on this yellow waveguide. This blue one is the sample, and yellow one is a waveguide. And here you have a microwave source, and that causes the and other part signal is actually goes to the reference, and then you can amplify this waveguide signal and compare with the Gauss meter, and you can have something curved like this one. So that's called FMR spectra that you must have heard, this ferromagnetic resonance spectra. So this is the a bit more detailing of the FMR, because the width is have various contribution. So that contribution coming some from the material, and some part is coming from the other fact like impurity and other factor. So this will be also shown here. So the some effect is inhomogeneity in a sample that present due to the formation of the defect, or some microstructure density, or it could be also the difference of the lattice parameter of the substrate and the thin film that you have deposited. So there are various causes of the inhomogeneous sources, but apart from that, there are other mechanism also. That's magnon and phonon scattering that associated with the material. That's again a deep condensed matter topic. So I'm not going detail of this magnon and phonon modes and its dynamics, but we can understood that these are a carrier for the dissipation of the magnetic energy. So magnon as well as the phonon, which is the quantum of lattice vibration. So both are associated with that. Now, depending on the material, you can see the various frequency ranges where absorption occurs. Not only that, you can have the various width in the material. So it's like now again become a very specific to the material, that what material you design, you will be making those devices. And then analysis of this curve, you can apply this LLG equation, that what most popular equation, that what called Landau-Lipschitz-Gilbert equation, and that you can use to simulate the experimental data to find the parameters that actually needed. So this is the critical formula that actually used to find, and this is the, again is finding the Gilbert damping, applying this formalism. So that we will do. Now coming to the material part. So as I say that we have used garnet thin film as a base material, and the reason for that this is a well steady material, and here can occupy various sites with the iron, so they can go to the two-head, decahedral, octahedral, or tetrahedral site. So all different type of atoms are available with the various coordination, and the light is constant is very high, so 20.376, which is generally 2.36. It's like one order of magnitude higher. But since it is a big molecule, so there are various number of atoms. So doing any simulation or analysis to this big molecular structure material, that's not easy. When you have perovskite, you are dealing with the 2 or 3 elements. Here, number of element is the same, but the size of the unit cell is very high. So that require more complex or rigorous calculation ability or computing ability to perform. And all theoreticians are actually required doing this kind of job. So that's another riddle dealing with this type of material. But nevertheless, this have most of the benefit that actually require to do this magnon-based devices, such as this very low Gilbert damping. So it can reverse its direction very fast. Minimum energy loss, that's what the welcome thought, that we want to have the energy efficient devices. So that's a welcome aside from this material. And also it is insulating in nature, that's another benefit. High TC, that's again advantage side, because you can make room temperature devices, because if your material transition temperature is very low, so no matter how beautiful that material is or what is the exceptional property is showing, making any devices that not very feasible option. So if the ordering temperature of material is above the room temperature, then only you can make any conceptualization of the making devices. And the things that more important for this material is a long magnetization spin diffusion length. So it's in some hundreds of micron to 10 millimeter. That's a very significant. So a spin wave can travel 10 millimeter without having any dissipation. So that's a unique ability of this garnet film. So tunable property, since it's a big molecule, so it's very easy to manipulate. Changing some atom or suppressing, applying compressive or tensile strain on this material, that's one feasible way that you can apply to change this. So now coming to the growth. So we first grow the material. So first, we try to optimize the garnet film that we grow in our lab. And first we consider our priority as a pure garnet without any doping, just to make sure that our reference sample is well understood. So we try to optimize this film using various thermal processes that what have been shown here. And then we characterize its oxidation state to see that how the oxidation state of the iron, yttrium, and the oxygen, which are the 3 basic elements of this garnet, are performed. And when we are satisfied with this finding, then we actually move ahead that structurally and electronic property of garnet is well established. So now we try to measure its magnetic property, and that's what you can see, that this history set that have been measured to find conventional magnetization behavior of this material. And this is a measurement done at room temperature. You can see that all the samples that what we have grown showing well behave ferromagnetic characteristic. Not only that, we apply the FMR, and you can see the resonance characteristic that coming into the field. So that's what that means. The garnet that we have prepared in our lab, they are well behaved. Not only that, we apply the LLG equation and Kittel fitting to find out the damping parameter as well as the effective magnetization. That's what have been seen here. So alpha value, that's what we are getting, is a 4.74 and 10 power minus 3. So then we try to search the literature that what is the best alpha value that people have reported using this method of the growth. So we found that our quality is far better than other previous observation that people have reported the growth using the similar growth method. So we were then confident that this garnet can be useful to do our desired experiment for the tuning. So we explored the literature and we found that they have used various material doping, like here manganese doping in the garnet or bismuth doping in the garnet. And they have proposed that this is the one effective method that one can utilize to tune the dynamics and the effective magnetization of the material. So we try to do the same thing. So we actually selected a thulium. The reason for thulium selection that it have ability to induce the perpendicular magnetic anisotropy, whereas the other literature that what other people have tried to do, they use material those shows only in plane magnetization. So our objective is not only changing the magnetic behavior, but also changing the anisotropy of material. Since if you have a material that shows a perpendicular magnetic anisotropy, so the device dimension minimization can be achieved much more easier than the in-plane devices. So we compare with our undoped garnet with the 1% doped, 4% and 7% doped garnet. And this is the AFM image. When we dope the thulium, you can see the modulation in the microstructure. It's a very, very pronounced. And all the doped sample, they are still obey the garnet structure that what have been shown in this X-ray diffraction data. So this is the, again, more detail about the structural property. So this is the SEM, that's scanning electron microscope graph that shows about the homogeneity of this material that you have in the grown by using the method that we use for growing material. So this length scale showing no larger defect, only this grain boundaries. So this is very obvious thing. Grain boundaries, we already aware that our sample is going to be polycrystalline. So grain boundaries are seen, but we don't see any other defect such as like cracks or some inhomogeneous patches. And we also did the EDX analysis to find the element proportion that their stoichiometry ratio are intact. So these were more detailed structural analysis in the terms of that is all the elements are distributed homogeneously throughout the field of view, or they are forming some cluster. So in this slide, we eliminated this presence of any clustering that taking place in our sample. So more detailed analysis of the phases. So this is the phase analysis. So for this, we actually did the Raman spectroscopy, and you can see and compare this the literature that people have found, and this our structure that what have been shown. If we compare the major peak, so they are actually coming to the same phase. So that's why we are pretty much sure that our sample is having these garnet phases. So we perform detailed magnetic measurement. So from room temperature to the 5 Kelvin, and you can see that they are well responding as very similar to the ferromagnet material. Now, when you go to the ultra low temperature, like below the 50 Kelvin, so you can see the some other effect taking place. Remember, now we have two different type of rare earth metal, one belonging to the thulium and another belonging to the yttrium. And at lower temperature, rare earth ordering are more prominent. So here you can see that there are some niggles appearing. And when we go to the 7%, when thulium is in more proportionate ratio, you can see the clearly bifurcation in this blue curve at a low temperature. So that's a compensation point, and after this, there the spin glass behavior can be realized, but we are not pretty much sure because we haven't performed experiment in that direction. But that could be a future measurement can clarify to us that this bifurcation is formation of the spin glass, or what could be the reason. Okay, so this is the another detail of the thulium doped garnet film, and as you can see, this is the XPS survey spectra. Now we try to compare that how the thulium doping actually affecting the yttrium binding energy, and that's what you can see that when 1% thulium, a red one is a 4%, and this blue one is a 7%. So as we are increasing the doping concentration of the thulium, yttrium binding energy is a influences. So that's what we can presume that thulium and yttrium in direct correlation, it's a dopant site. So thulium is directly replacing the yttrium site in the garnet lattices. So these are the FMR spectra that we have recorded for all the samples. And not only that, we have also compared with the undoped sample in this case here. So that's another detailed analysis. That's what we did for 1%, 7% using the Kittel formalism to find out this type of graph that details that how the resonant frequency, line width are changing with respect to the doping of material. Not only that, we also perform the angle dependent measurement, means changing the angle between magnetization and the sample orientation. We can tweak the angle. So how the angle varies in the terms of the line width, that's what have been also shown nicely in this graph. Then it comes to this final graph. That's what we extracted out after all analysis, so that you can focus to only this part. So here you can see the effective magnetization that have been shown by black curve. This is decaying when we are increasing the concentration of the thulium. And if you look this blue part, that's a Gilbert damping. It is increasing as we go to the higher concentration of the thulium. So actually, this experimental finding actually key demand for the having such material that can suit for designing the any devices using this spin-based concept or spin-based devices. So now it's the time to recap my presentation. So I hope I'm able to convince you with our experiment that we are able to generate a new series of the garnet thin film. And due to the thulium-based spin engineering can induce a certain manipulation in the spin damping, and also the demagnetization field shows a very identical trend. So this series of the garnet can have the bizarre ability to design a next generation spintronics and magnon-based devices, which is the key foundation for the quantum mechanics. So with this, I would like to thank you for your kind opportunity and this nice audience and listening interest in this talk. With this, I would also like to thank our grant agencies such as DST Nano Mission and DST Device Development Program, Shakura Grant, as well as now currently we are running a project from ISRO, as well as some international cooperation by various agencies. With this, I would like to thank you again for your attention.
Thank you, sir.
Yeah.
Dear participant, if you have any question, please ask. Sir, I have a question. What are the primary material science challenges in the scaling up quantum devices that rely on magnetism?
Yeah, I think there are various materials that you can think that can realize this quantum mechanics. Like all the superconductor, that's what people work. So that's like a non-spintronic material. But most of the superconducting phenomena that you are seeing, that's purely driven by the quantum mechanics. So classical conceptualization cannot explain the superconductivity. And that's what the BCS and other theory have come across, that try to explain that how the superconductivity evolved in some of those complex materials. So those materials are not very straightforward. And mechanism is still people are thinking the BCS theory is one theory that can explain all the superconductivity. But people have doubt that this is the ultimate theory. People are still looking for optional theory, that even more advanced version. But still, I think this BCS theory is one of the most advanced way that you can describe this quantum behavior of the superconductivity in this material. On spintronics part, I talk about garnet, or non-garnet samples are also present there. People are using now 2D electron gases and 2D materials, where they can conceptualize this quantum behavior. So 2D material is also a new dimension that just recently opened from the last 2 decades, and people are seeing various phenomena in 2-dimensional material, and thanks only to the quantum technology or quantum mechanism.
Thank you, sir. Thank you very much, sir. On the behalf of the organizing committee and all participants of this AICT ATAL sponsored FDP, I extend our heartfelt gratitude to Dr. Kumar Mishra, Associate Professor, IIT BHU RRC, for delivering such an enlightening and engaging session on magnetism for quantum device technology. Sir, you in depth explanation on the quantum magnetism, spintronics, and their application in advanced devices design have provided participants with a deeper understanding of how magnetic materials are shaping the future of sustainable and energy efficient technology. We sincerely thank you for sharing your time, expertise, and valuable insight with us. Thank you once again, sir, for making this session truly inspiring and impactful. Thank you, sir.
Thank you very much. Thanks for once again for opportunity.
Thank you, sir. Dear participant, there is a 5-minute small break. The next session start in 10 minutes.